Hello, I am Gopi Deshpande from Auburn University MRI Research Center, where I'm an associate professor. Today I am going to talk about a recent paper that was published in Magnetic Resonance Imaging, where we showed that hemodynamic response function variability actually confounds resting state fMRI functional connectivity. The background for this is that, as everybody knows, fMRI is an indirect measure of neural activity obtained from blood hemodynamics and it can be construed mathematically as a convolution of the hemodynamic response function, or the HRF, and some kind of latent neural response which is not measured. And most fMRI functional connectivity studies actually assume that every voxel in the brain has a standard canonical HRF during their analysis. However, recent advances have shown that this HRF is variable for different brain regions and also across individuals. This raises the questions regarding the reliability of functional connectivity results, since it is unclear if observed changes are really due to neural activity or due to HRF variability. And this is illustrated in this diagram, where you can see the top row represents latent neural signals from two different regions of interest, and this is actually from the data. And the HRF corresponding to those two different voxels. And the bottom row actually shows the bold fMRI signal. And on the left-hand panel, you can see that even though the two time series don't have a lot of correlation, R is equal to 0.38. However, because their HRFs are different, they have different shapes, they could actually be very highly synchronized in the latent neural space. And the opposite was also true, as shown on the right-hand panel, wherein the time series are really not correlated, just R equal to 0.07 in the latent neural space, because, however, the difference in HRF shape between the two voxels is such that it tends to synchronize these two signals, and you get almost near perfect correlation in the bold time series. So this kind of intuitively shows what this problem is, and therefore, based on this, we tested the hypothesis that HRF variability actually confounds functional connectivity estimates. And in this paper, we're specifically looking at the brain's default mode network. So the theory behind this is actually quite straightforward. As I said before, the bold fMRI signal can be construed as a convolution of the HRF with some kind of unmeasured latent neural time series plus some measurement noise, and this can be represented in the discrete frequency domain. And you can see, I'm not going to go through that in this entirety, but as you can see, if there is some kind of delay in the HRF, and if these delays are different for these two different voxel time series, then the functional connectivity that you estimate in the bold space is actually different from the functional connectivity that you would actually get in the latent neural space, theoretically speaking. So let's see how we went about testing this hypothesis. The data was acquired from 47 healthy subjects here at the Auburn University MRI Research Center, and we used Siemens Magnetom 70 scanner. So this was actually a 70 study, and multiband EPI, multiband factor of 2, 11-minute scan, and a TR of 1 second. All standard pre-processing steps were performed, including bandpass filtering and regressing out different sources of unrelated variance. And then we extract mean time series from 58 regions of interest, which corresponding to the default mode network as defined by the Power Atlas. Methods, we did both simulations to see how the method performs, and also actual experimental data. And if you look at the simulations, what we did was basically adopt the procedure shown in reference 4, wherein we simulated pairs of neural time series with known neural functional connectivity between them, then simulated pairs of HRFs with known HRF differences between them, and then convolved them to obtain pairs of fMRI time series, and then we calculated the functional connectivity in the fMRI space. Then what we did was to compare the percent difference between the neural functional connectivity, the ground truth that we knew, and the fMRI connectivity, and this is called delta FC, or difference in functional connectivity. And then we saw how that corresponds with different HRF parameters. With actual experimental fMRI data, HRF parameters were actually estimated through blind deconvolution. Obviously, here we just have the bold measured time series. We don't know what the HRF is for that specific voxel. We also don't know what the latent time series is. So this kind of blind deconvolution technique that was proposed by Wu et al. From Daniel Marinazzo's group, and they're also co-authors on this paper. So we use their method to extract the HRF shape from resting state data, and the HRF shape was characterized by three different parameters: response height, time to peak, and full width half max. And then what we did was find functional connectivity, resting state functional connectivity, using Pearson's correlation from two different pipelines. One was data with deconvolution. This is HRF variability minimized data, and then data without deconvolution, which is the raw fMRI data, and this is HRF variability ignored data. And for this, both deconvolved and non-deconvolved functional connectivity networks were compared using a paired t-test, p less than 0.05, and it was Bonferroni corrected, very conservative, along with regional HRF parameters revealing potential false negatives and false positives that results from HRF variability. I say potential because, in experimental data, we don't know the ground truth. If you look at the results, using simulations, we actually found evidence supporting our hypothesis, as well as experimental data that I'm going to go next. Let's first talk about the simulations. We found that the variability in response height and time to peak, and of course this variability was simulated such that it's within the biologically plausible range. It caused change up to 50% in functional connectivity. And as you can see in the next slide, the panel A actually shows percent difference between time series response height on the x-axis. On all panels, the y-axis is the percent change in functional connectivity. And you can see there's an increase in differences between functional connectivity within deconvolved and non-deconvolved data when there's a larger difference between the response heights of the HRF. Same is true with time to peak, same order of magnitude difference. The trend is there for differences in full width half max, but the order of magnitude is much smaller. I think the important point is take-home message is from panel D, wherein you can see that the absolute value of neural connectivity actually has a bearing on what is the difference you get in functional connectivity. I mean, it can be up to 170% when the absolute value of functional connectivity is smaller, which is like weaker connections, but it can be even up to like 22% even when the functional connectivity is large, like more than 0.75. So I think that was very illuminating for us. Let's move on to results from experimental fMRI data, wherein we identified several potential false connectivities which is attributable to HRF variability. Majority of the connections were between different lobes, and we think that this is probably because of larger variability in vasculature between the lobes, which affect the HRF. So the next slide actually shows where these connections are. And as I was saying, you can see they are all between different lobes. The top row shows pseudo-negatives, and the bottom row shows pseudo-positives, and it's noteworthy that there are more pseudo-positives than pseudo-negatives. Next, we can actually look at the histogram of this percent connectivity difference between deconvolved and non-deconvolved data. And what we see is that HRF variability caused almost like a mean of 14.7% and a median of 9.6% error. So what is noteworthy here is there are a large number of connections which have smaller errors, but the number of connections which have large errors is not negligible, and many a times these are the ones that we are interpreting. So I think that needs to be kept in mind. Finally, we found a double exponential relationship between the magnitude of HRF variability and its impact on functional connectivity. And it suggested that, for example, if you look at the next slide, the double exponential curve, 1/3 of the connections had at least 10% change in connectivity, and 10% of the connections had at least 1/3 change in connectivity. due to the HRF variability. So this kind of gives you a sense of what is the impact of HRF variability on functional connectivity estimates from resting state data. Even if we contend that the ground truth HRS were less variable than what we assumed, or that our deconvolution estimates were considerably noisy, we would still observe nearly prominent effect of HRF variability. I mean, as you can see here, the red curve is what I showed you before, which is results from all connections. And if we just looked at the bottom 25% of connections with least HRF difference between regions, and it still has, the curves obviously shifts a little bit, but still there are a large number of connections with there's I think a substantial number of connections with errors. Let's discuss these results. So if we look at our findings, it implies that HRF variability on average causes about 15% error in functional connectivity in healthy adults for the scan parameters we have used in a 70 scanner. What's disconcerting is that the results could be worse at 3T, because we know that the higher the field strength, you're more sensitive to smaller vessels. So the HRF variability could be smaller. I mean, this really needs to be tested at 3T and see what happens. And the error of the order of 15% in connectivity estimates, I think, is sufficient to cause a large impact on statistical inferences. So this is really the error in magnitude. I mean, because in functional connectivity, we're not looking at directions. And the network and this impact could not just be on statistical inferences, but also probably on network structure, on graph analysis, and machine learning models, and many other derived measures such as behavioral associations. I think what needs to be emphasized here is that even in psychiatric and neurological disorders, aberrant changes in connectivity are often of this magnitude or smaller. So I think this is very important to keep in mind. Also, the results imply that HRF variability could lead to the identification of potentially false positive and potentially false negative connections, and that functional connectivity findings from HRF variability ignore data, which is basically pretty much everything that people are doing these days. I think they should be interpreted cautiously. And we hope that our study encourages researchers to overcome this perplexing lack of attention, I think, to HRF variability while studying fMRI functional connectivity from resting state data. This is an error in magnitude, so and I think the error in magnitude for the kinds of things that functional connectivity is being used these days, for predicting age as functional connectivity fingerprinting, for that kind of analysis, I think this error is going to matter, and there should be more attention to this aspect in future research. Thank you for your attention, and these are all the references for anybody who are interested. And I would like to thank my co-authors and also the MRI Research Center and the funders for this study. Thank you very much.